Hello, friends, and welcome to yet another lecture on operation research. Today, we'll take up an yet another interesting problem. Now, this problem is about a network, and you have a network, and you use the critical path method to solve the network. Okay, so the solution is given how to use the critical path method to solve a network. Now, we'll go into these steps where we'll see what is a network. Why do we use critical path to solve a network? Well, in short, just remember one thing. A network is nothing but a nodes and activities require time. Now, this is used to represent a project where a project has a start, the project has a finish. Now, how do we use the critical path method to find out what activities are critical so that if we delay those activities, okay, the activities which are on the critical path, if they are delayed, it leads to delay of the entire project. So we need to identify this critical path, and this problem is all about that. Okay, so without much delay, I am Professor Arvind Prasad. Let's begin. Okay, so usually you will be given such a table where you will be given the activity on the left hand side, and then you will be given the A, B, and M values. Now, what are these A, B, and M values? Now, A is the optimistic time of completing the project. That is, it is the time which is the least amount of time that is required to complete any activity in the project. Now, B, of course, is the pessimistic time. So, the pessimistic time is the time which is the slow time to complete the project. That is, how far a project can be delayed or how slowly it can be performed. And M, of course, is the most likely time. Now, in this particular problem, for the activities, A, B, and M are in weeks. So, of course, to calculate the time, that is the average time, you have Tij, that is the time required for any activity 1, 2, where I is 1, j is 2, where I can be 2, j can be 3. These are the indices for the activities. So the time required to do any activity is nothing but a plus 4m plus b divided by 6. And the variance of the time is given by b minus a the whole square by 36. We'll take up this question of variance at the later stage. So let's look at the activities first. Now we have the activity 1, 2, A, B, and M are 4, 8, and 6. And if we use the formula A plus B plus 4M divided by 6, we get 6. Similarly, for activity 1, 3, it's 13 by 3. Similarly, for activity 2, 4, it's 10 by 3. And so on and so forth. We go on till the activity 8, 9, where it is 53 by 6. Okay, so we proceed from here now. Now we draw the network diagram. Now in this network diagram, what you see is you have circles which have numbers and you have arrows which have numbers also written near them. Now the arrows are the activity. So the activity 1, 2 is represented by this arrow and the time for this activity is 6. Now the circle 1 is node 1 and the circle 2 is node 2. So when you want to go from node 1 to node 2, the activity is 1, 2. Now if you want to go from node number 1 to node number 3, the activity is 1, 3. Now this is a network diagram and it gives you a clear view of the sequence of activities. Okay, so here what we have is, we know that the activity 1, 2, and 1, 3, they are the starting activities. Activity 7, 9, and 8, 9, they are the ending activities. And in between, we have all the intermediate activities. Okay, and the timing for these activities are given to you. So if you perform activity 1, 2, you go from node number 1 to node 2. If you perform activity 5, 7, you go from node 5 to node 7. Now, the questions that we have here is, what is the estimated time for the completion of the project? We have done the network diagram But from this, how do we find what is the estimated time for the completion of the project? And also, in our own life, we may have experienced this, that there are certain tasks. Whenever you do any program, whenever you execute any program, a program is nothing but a sequence of activities. So whenever you do any project or program, you will always find that certain activities are pretty critical. Critical in the sense that if we delay in performing them, or if we take more time in performing the activity, we may have a plan of performing our activity within a certain amount of time. But then if we delay, we extend it, the entire program or activity is extended. But then there are also certain activities we may find that delaying them is okay. It really does not affect the overall completion time of the program or the project. So we have to identify such critical activities, number one. And number two is, of course, we have to also estimate what is going to be the completion time of the project. Now, how do we go about doing this once we have drawn this network diagram? So for this, we do something is we calculate the early event time for nodes. Okay. So we have in total 9 nodes here, that is from node number 1 to 9, and we find the early event time for each node. Now, what is the early event time for each node? Let's look into it. Now, the earliest we can come to node number 1 is 0, because that's the starting node, of course. Now, the earliest we can arrive at node 2 is 6 weeks, because from node 1 we go to node 2 and it takes 6 weeks to reach there. So we can see here, okay, and we can see here too. So it takes 6 weeks. Now the earliest we can arrive at node 3 is 13 by 3 weeks. So I have noted down that here it's 13 by 3 weeks. Now it gets interesting once we come to node 4. Node 4, if you go to see, there are 2 activities which reach node 4. One activity is activity 2.4 and the second activity is activity 3.4. Now, what is the earliest event time that we can give to node 4? That is the earliest from node 4 that we can proceed for all other activities. Remember, what I make myself very clear, that from node 4, what is the earliest we can proceed towards going to node 7? Okay. Now that we are coming from 2 to 4 here and 3 to 4 here, right? There are 2 activities which are coming to node 4. So what we do here, to calculate the early event time, we take the early event time of 2 and to it add the activity time of 2 and 4, 2 to 4. Similarly, we take the early event time of 3 and to it we add the activity time for 3.4. Once we have done that, we find the maximum of that, and that is the early event time for node 4. So that's going to be 40 by 3. Now, what does this mean? What it means is, out of these 2 competing activities, we have to see which activity takes the maximum time to reach here at 4. Of course, we have to take the early event time of the predecessor nodes, okay, into account for that. So we are taking enough time, we are giving enough time from 3 to 4 so that task 2.4 is also completed and task 3.4 is also completed. Of course, when we come from 2 to 4 and 3 to 4, we will always see which takes the highest amount of time to reach. Okay. And that is going to be the time where from earliest we can start from 4 to 7. Okay. A similar explanation goes in for node 7 too. Now we have calculated it. So after calculation, we finally come to node number 9 this way. Okay. I have already shown how we calculate node number 2, node number 3, node number 4, 7 also I have discussed. 4 to 5 is again, if you want to calculate 5, you have to take the early event time of 4 and to it add the time which takes from 4 to 5. So finally we get 223 by 6, which is roughly around 37.2 weeks. So this is the earliest time we can complete our entire project. Now, this is something of what we have done now so far, and we are now in a clear position that what is the earliest we can complete our project. Now, what if we ask a scenario, what if you are given lesser than 37 weeks to complete the project? Or what if you are given greater than 37 weeks to complete the project? What is the probability of success that you might end up doing it? That's question number 1. Okay, now for this, we need to know which activities are critical, the activities which cannot be delayed. That is the first thing we need to know. So how do we go about it? We go about it by finding the late time. Okay, that is LT. Now, what is late time? So late time or late event time is time you start calculating in the backwards fashion. Now, we know that the early event time to reach node 9 is 233 by 6. Now we start moving backwards to calculate the late time of 8. Once we calculate it, I'll explain the logic of what it means. To calculate the late time of 8, we take the late time of 9. Okay, that is 223 by 6. And from that, we subtract 53 by 6. Okay. So this means that the latest we should come to node number 8 is 85 by 3 weeks. This is the latest we should arrive at node number 8. Now, coming back to node number 7, it's going to be late time of node 9 minus 15. Okay, so that's going to be nothing but 133 by 6. We still calculate that we have calculated for 8, we have calculated for 7, 6 goes similar. We take the late time of 8, subtract 10 by 3 of it. Now 5, for 5 we take the late time of 7 and subtract 2 from it. Right? For 4 we take the late time of 7 and subtract 53 by 6 of it. So this is what we get. Okay? 25, 121 by 6 and 40 by 3. Right? Now let us come to late time 3. To come to 3 in the reverse fashion, you have to remember one thing. There are 3 paths coming to 3 now. Now that is, one is coming 9, 8, 6, 3. The second path is 7, 5, 3. And the third path is, of course, 7, 4, 3, starting from 9. So we have 3 paths which are finally coming and converging at 3. Now, what is going to be the late time at 3? Now, the late time at 3 is going to be the late time at 4, the late time at 5, and the late time at 6. Written here, late time 4, late time 5, and late time 6. And from this, we subtract the time required to come from 4 to 3, which is nothing but it's going to be time required to go from 3 to 4. That is 9. And the time required to come from 3 to 5, which is again going to be 5 to 3, which is going to be 10. And similar, we are going to say for 3 to 6. The plus here is a mistake. That's a typo. It should be minus here. Just take care of that. Okay. So it's going to be LT4 minus 9, LT5 minus 10, and LT6 minus 73 by 6. Now we take the minimum of this. Okay. So the minimum of this is going to be LT3. Right. The minimum is going to be LT3. That is from the previous one. What it takes the minimum time to come to the predecessor, because that is the latest we can drag the predecessor close to the next event. Okay, that's the logic behind it. So we calculate the LTs, and once we have calculated the LTs, now we come to another concept, that is total float. Now total float for any activity is going to be, or any activity, let's say 1, 2, is going to be the LT at 2 minus the ET at 1. Right? So let me explain this further. The total float for this activity, this particular activity 1, 2, is going to be the LT at 2 minus the ET at 1. If you want to find the total float of this activity 2, 4, it's going to be the LT of 4 minus the ET of 2, and from that, of course, you have to subtract the times. So the calculation is shown here. Any LT is going to be, or any total float is going to be the LT of j minus the ET of I minus T I j. Okay. For activity 1, 2, it's going to be 4 because LT2 is 10 and LT1 is 0 and Tij is 6. So you have 4. Now, what does total float mean? We started the early time for node 1 was 0. If we have a total float of 4 here, it means that we can come to the late time of node 2 by starting 4 weeks later. Even if I start from node 1 4 weeks later, I will reach at the late time of node 2. Right? I will reach to the late time of node 2. Let's take another one, that is 2, 4. Now here the total float again I have calculated is 4. Now the early time is 6. Right? And the late time here is 40 by 3. Okay. So I can technically, instead of week 6, delay till week 10 and still start and come to the late time of 4. This is what it means. But if you find that the total float for certain activities is 0, it means these activities you cannot start late. You cannot have a delay. You have no leeway or slack in doing these activities. Now, these are known as critical activities. Now, if you see, the critical activity here is 1, 3. This is followed by 3, 4. This is followed by 4, 7. And this is followed by 7, 9. So, if you look in the network diagram, the red arrows are the arrows which are the critical activities. So, from the start to finish, the red arrows are something of the critical activities. Now, these activities are activities which you cannot delay. If you delay on these activities, if you do not follow the time schedule of these activities, you will end up delaying the project. If there is a delta delay in any activity in these red arrow activities, that much time of delta, the project will also get delayed. This is what it means by critical activity. And the critical path, of course, is 1, 3, 4, 7, and 9. So the duration of the critical path, of course, can be calculated by summing up the critical activities. So that's again, interestingly, 223 by 9. That is the early time of the project. And what if I ask you a question, what if instead of 37.167 weeks to do the project, I give you 40 weeks? What is the probability of success? Will you be 100% successful? Or is the probability that it's going to be 1 and you're going to be really successful in doing it? Or is the probability something else? Now, let's see. This is a very interesting thing to ponder on. Now, what happens is, let's see what is going to be the probability of finishing it in 36.167 weeks, which is 223 by 6. So the probability is found by taking the time by which you are going to complete minus the critical time divided by the standard deviation of the critical paths. Right? Now, what is going to be the standard deviation of the critical path? For this, first, what you do is you add all the variances of the critical paths. So that I have done here, the critical activities which form the critical path are 1, 3, 3, 4, 4, 7, and 7, 9. So I find the variance. The variance is nothing but, let me show it here in the formula, b minus a the whole square by 36. Okay, so I calculate the variance of the critical path there and I sum it up. After I sum it up, that is, the sum is here, I take the square root, so I get the standard deviation of the critical path. Now let's get to this formula. Forget putting 40 here, just put 223 by 6 here, which is nothing but the early time of the project that we had calculated. So the difference of this is going to be 0 and this divided by this is going to be 0 and P0. So P is something of you have to look into the Z table. So what is Z table? Z table is nothing but a normal distribution where the mean is 0. Okay. And you have a symmetric standard deviation along 0 on both the sides. So you have standard deviation 1, 2, 3, 4, standard deviation 1, 2, 3, 4 spreads, and it is a bell-shaped curve along that spread. Right? So if you go to see, the probability of 0 is going to be 0.5 if you look up into the Z tables. What does that mean? That means that the probability that you will complete it in 37.167 weeks is 50. Well, you might find it surprising. Why? What does it mean? Why is it that way? Well, it means that way because there is a 50-50 chance, because this is all a probability. Remember one thing, here what you have done is you have taken a mean of the optimistic time, the pessimistic time, and the mean time and calculated the times. So these are nothing but probable values. So the probability that you will finish the project in the critical time is 50%. Now the probability that you will complete it in 40 weeks is higher. It's 0.87365 because you take 40 minus 223 by 6 divided by the standard deviation. Okay. And this value, you look it up in the Z table for the probability. And what you find is it is 0.87365. So it means it's higher. You have an 87% probability that you will complete it in 40 weeks. Even if you took a higher amount, remember one thing, the probability would never be 1. It would tend to 1, but never be 1. Because at the end of the day, you have made probabilistic estimates of the time for the project. So you are going to get a probabilistic reply for the success of doing it successfully in the time you choose to, whether it's going to be within the critical time, greater than the critical time, or lesser than the critical time. So that was all about how do you use the critical path method to analyze a network. With the critical path method, you can find out which activities are critical. And of course, by drawing the networks. Now, this is known as a program evaluation and review technique. By drawing such a network, Okay, by taking probabilistic time and calculating the likely times from going from 1 to 2, 2 to 4 and all, calculating the times. What you are trying to do is you are trying to make an estimate, program evaluation. Okay, you are doing a program evaluation and you are reviewing it. You can review it by changing times. If you change the time, what is going to be the effect on the project? You can very well do on this network. So this is known as a PERT network, or this is known as a PERT network diagram. Okay, and to find critical path in this, you use the critical path method, which we have done here. So this is the critical path method. So that's the end of my lecture. Hope you enjoyed it. Hope it was informative to you. So do like and subscribe my channel. Goodbye. Have a great time.